Hello, everyone. Welcome back to ILTA Physics, where we master physics through problem solving. Today, we are going to study accelerated motion together. Accelerated motion is simply any motion where an object's velocity changes over time. Take a look at the image below. These are snapshots taken at constant time intervals of a bicycle starting from rest. At first, the velocity is slow, but as it picks up acceleration, you can see the bicycle traveling a greater distance during each equal time interval. Just like this, acceleration is a very important kinematic quantity that helps us explain the various movements of objects we see in our daily lives. The problems we'll solve today focus on motion with constant acceleration. We will look at the relationship between the change in velocity, the change in position over time, which is displacement, and how these variables connect. We are going to solve these various problems using the appropriate kinematic equations. Since accelerated motion is a fundamental part of classical kinematics, it's essential to understand the core of each problem type and organize your thoughts through plenty of practice. Let's start by quickly reviewing the basic concepts and kinematic equations needed for accelerated motion. Here is a summary of the physical relationships of accelerated motion expressed as quantitative formulas. I've already explained these in detail in my theory lecture, so I'll just briefly summarize the resulting formulas here. To keep the equation simple, let's assume the initial time is 0 and represent the time interval simply as t while we derive the formulas. First, by definition, acceleration is calculated as the rate of change of velocity over time. In other words, it is the final velocity minus the initial velocity divided by the time interval. Since we are dealing with constant acceleration, we assume this value is a constant. The change in velocity for this type of motion can be calculated by rearranging the definition of acceleration. It's the product of acceleration and time. Therefore, the final velocity equals the initial velocity plus acceleration times time. Next, the change in position, or displacement, in constant acceleration motion can be seen as the shaded area on a velocity time graph, as shown in the diagram on the right. This displacement comes from two parts of the motion. To be precise, it consists of the v I times t part, which represents constant velocity motion if the initial speed were maintained, and the 1/2 t squared part, which represents the additional distance covered due to the change in velocity from acceleration. Accordingly, the final position of the object is the initial position plus the displacement from the accelerated motion. This results in a quadratic equation with respect to time, which might look a bit complex at first. However, if we set the initial position to 0, meaning we start at the origin of our coordinate system, the first term disappears and the formula becomes simpler. If the initial velocity is also 0, meaning we start from rest, it simplifies even further into a basic quadratic expression. Now let me give you a very important tip for solving problems. If you know both the initial and final velocity of a moving object, you can calculate the average velocity. The average velocity is literally the average speed of the object during the time interval. So, the displacement can be calculated simply by multiplying the average velocity by the time interval. In many problems, you'll be able to find the initial and final velocities easily. In those cases, using the average velocity is often much simpler than dealing with the complex quadratic equation for time. Finally, by combining these various equations, we can derive a formula that relates velocity and displacement without involving the time variable. If a problem doesn't give you specific conditions of time, approaching it with this velocity-displacement relationship is a great strategy. If you don't fully understand the meaning of these physical relationships yet, I highly recommend watching my theory lecture first to grasp the constant acceleration equations before coming back to these problems. Now, let's dive into some constant acceleration problems. Problem number 30 is about the acceleration of a flea jumping from a stationary position. This specific problem type is one where no time information is provided, so we should use the relationship between velocity and displacement. Another thing to watch out for. This problem isn't about the flea while it is already in the air. It describes the accelerated motion from the moment the flea crouches until the moment it fully extends its legs to take off. Please refer to the diagram on the bottom right. The problem states that the flea starts from rest, and its velocity at the moment it's about to leave the ground is 1 meter per second. The displacement during this takeoff is 0.5 millimeters. First, let's find the acceleration. While acceleration is defined as the change in velocity over time, we don't have time information here, so we will use the velocity displacement formula. Final velocity squared equals initial velocity squared plus 2 times acceleration times displacement. From the given conditions, the final velocity is 1 meter per second and the initial velocity is 0. Substituting the displacement of 0.5 millimeters into the formula and solving for it, we get a massive acceleration of 1,000 meters per second squared. Now we can find the time it took in two different ways. First, using the relationship that the change in velocity equals acceleration times time, the time taken for acceleration comes out to 1 millisecond. Alternatively, if we use the relationship between displacement and average velocity, the time for acceleration is still calculated as 1 millisecond. I hope you practice using the most appropriate formula based on the given conditions like this. Problem number 33 is about deceleration. Deceleration is the opposite of acceleration. It's when an object's velocity decreases over time. In this problem, a skier slows down from a velocity of 8 meters per second to 6 meters per second while sliding over a distance of 5 meters. We need to find the acceleration. Again, since there is no mention of time, we use the velocity-displacement relationship. The final velocity is 6 meters per second, the initial velocity is 8 meters per second, and the distance traveled is 5 meters. If we plug these into the formula, the acceleration comes out to negative 2.8 meters per second squared. The question asks for the magnitude of the acceleration, so the answer is 2.8 meters per second squared. Let's think about an important physical concept here. A negative acceleration value doesn't automatically mean slowing down. It means the acceleration is acting in the opposite direction of the positive direction we've established in your coordinate system. To summarize, whether an object speeds up or slows down depends on the relative directions of velocity and acceleration. As shown in the diagram below, please understand that even if the acceleration is negative, if the velocity is also negative, meaning they are in the same direction, the object will actually speed up. On the other hand, if the velocity and acceleration are in opposite directions, the object will slow down. Make sure to clearly understand this concept of velocity change through the theory lectures. Problem 34 asks about the travel distance during accelerated motion given the ratio in velocities between a propeller plane and a jet plane. Many students find it difficult when conditions are given as ratios, so please pay close attention to this explanation. The problem asks for the relationship between velocity and distance without mentioning time. According to the formula relating velocity and displacement, if the initial velocity is 0 and the acceleration of both objects is the same, the travel distance is proportional to the square of the velocity. Therefore, if the jet's velocity is 2 times faster than the propeller plane's velocity, the distance traveled during that time will be 2 squared, which is 4 times greater. So the answer is 4 times 1/4 of a mile, which equals 1 mile. Let's calculate this more quantitatively. Based on the velocity displacement formula, the distance traveled by both objects can be calculated as the square of their respective velocities divided by twice the acceleration. Since the problem says the jet's velocity is twice the propeller plane's velocity, substituting this into the equation shows the distance is indeed 4 times greater. So, if the propeller plane travels 1/4 of a mile, the jet's distance is 4 times that, making 1 mile the final answer. We have now walked through various types of problems involving accelerated motion. Please keep practicing so you can choose the right formulas for the given conditions. That's it for today's lecture. Great job, everyone. I'll see you in the next session.